Hi dear students, this is the sixth part of fourth module of the subject ME 206 Fluid Machinery. In this presentation, we will see effect of pipe friction on the pressure head inside the cylinder. In the part 5, we have seen the effect of acceleration of the piston on the pressure head inside the cylinder. Now we will be seeing the effect of pipe friction on the pressure head inside the cylinder. So since the water is flowing through the suction pipe and the delivery pipe, there will be some frictional effect while the water is flowing. So for that frictional effect will produce some pressure head inside the cylinder, or in order to overcome that frictional effect, some more pressure is to be produced inside the cylinder, then only the required suction and delivery will be completed. As water flows through the suction and delivery pipes, there will be a frictional resistance into its motion. At any instant, if the velocity of the water in the pipe is v, then head loss due to friction is given by the equation HF equal to 4FL v square by 2GD. As we all know, this equation is very much familiar to us, Darcy-Weisbach equation. So in that equation, if v is the flow velocity, whether it may be suction or delivery pipe, then the head loss due to friction is given by 4FL v square by 2GD. For F is frictional coefficient, L is length of the pipe. If we are calculating the head loss due to friction in the suction side, then L will become length of suction pipe LS, and small d is the diameter of the suction pipe, that will become ds, and 2g everything you will be knowing. So V only is the value we have to substitute, where F is the pipe coefficient. But V is equal to A by A omega R sin theta. This equation we have derived in the starting of the derivation of the pressure head inside the cylinder due to the acceleration of the piston. In that section we have derived this equation. I think you will be remembering taking that distance x and all, total distance you have written in terms of radius, and finally distance x you have found out. By differentiating that distance you will get the velocity. Please scroll back and see how this equation has came. V is equal to A by A omega R sin theta. Actually it is V is equal to A by A omega R sin omega t. Omega t is theta, therefore we are writing V is equal to A by A omega R sin theta. If this particular section is asked for higher mark, more than 6 mark or 5 mark, then definitely you have to, you can't write this equation directly here. Instead of writing this equation directly here, you have to derive this part also. You can refer the earlier presentation. Okay. Now anyway, we have already done this, and that's why I am directly using V is equal to A by A omega R sin theta. Now substituting for V in the Darcy-Weisbach equation, we will get HF equal to 4FL by 2GD into A by A omega R sin theta whole square. Now at the two ends of this, that is the head loss due to friction. Now at the two ends of the stroke, that is theta equal to 0 and theta equal to 180 degree, that is the theta value at the starting and end of the stroke, whether it is suction or delivery. Now at here the term we have is having sin theta term. So sin theta will be 0 at the starting and at the end. Theta equal to 0 degree and 180 degree, sin theta will be 0. So at the starting and end of the stroke, whether it is suction or delivery, there won't be any frictional head inside the cylinder. But as the theta increases, the frictional effect goes on increasing, and it will have a maximum value at the middle of the stroke, that is theta equal to 90 degree. Since at that time the sin theta value, sin 90 will become 1. So that is the maximum value. So the maximum value at the middle of the stroke, that is theta equal to 90 degree, will be HF max equal to 4FL by 2GD into A by A omega R whole square. Sin theta became 1. Now this will be the maximum, and remember this is the maximum frictional value, and this will be acting at the center of the middle of the stroke, that is theta equal to 90 degree. To overcome this frictional resistance, there will be further pressure variation inside the cylinder. Now thus, considering the effect of acceleration of water in the pipe as well as pipe friction, the pressure head in the cylinder is given by the following expression. Now we are combining everything together. During the suction stroke, the absolute pressure head inside the cylinder will be, we will have the pressure head inside the cylinder will be always less than the atmospheric pressure during the suction stroke. So H at ATM, H atmospheric minus Hs, this term is constant. That is that rectangle. I think you will be remembering that indicator diagram, that rectangular part, HATM minus Hs. Along with that, you will have the pressure head due to acceleration, that is Ls by G A by A omega R cos theta, minus, along with that you will have the pressure head due to friction, that is 4F Ls by 2G ds. Actually here it should be 2G ds, suction pipe diameter into a by a omega r sin theta whole square. See, this acceleration term is depending on cos theta, and the frictional term is depending on sin theta. At the during the delivery stroke, also we will have the minimum pressure will be HATM plus HD. That will be always the pressure will be above the atmospheric pressure line. That's why plus is coming. Plus acceleration head is added along the delivery side, LD by G A by A omega square r cos theta. Along with that, we will be adding the frictional effect also. So in the suction side, we will be subtracting acceleration effect due to friction and acceleration effect due to acceleration of the piston, whereas in the delivery side we will be adding both these quantities. The reason and all I have explained in the last presentation. Since the suction line is drawn below the atmosphere, if you consider the indicator diagram, the suction line will be below the atmospheric pressure head. Along with that, atmospheric head pressure head due to acceleration is added. To that again one more loss is added, that is head loss due to friction is also added. So both are getting added, means the top pressure inside the cylinder is going further and further below atmospheric pressure, or going more towards the vacuum side. That's why it is subtracted. Considering the delivery side, it is getting added. That's all. Okay, I think the concept is clear for you. Now this is the indicator diagram, effect of friction on the indicator diagram. We are not considering here the acceleration pressure due to the acceleration of the piston. Here we are considering only the effect of friction on the indicator diagram. This basic rectangle ABCD was our earlier ideal indicator diagram. Along with that, during the starting of the section, as I have explained, theta equal to 0 degree, so sin theta is going to be 0, so HF is 0. At this point HF is 0, here also HF is 0, here also HF is 0, here also HF is 0, and at the middle of the strut the HF value will be maximum, that is equal to A by A. I have already explained that maximum value is 4FL by 2GD A by A omega r whole square. This will be the maximum value of the HF. In the suction side, HFS max equal to 4FLS by 2GDS A by A omega r whole square, and at the delivery side HFD max will be 4FLD by 2GDD into A by A omega r whole square. That is the only difference. That length and diameter term will be substituted corresponding to suction as well as the delivery side. So here you will have that the theta equal 90 degree, here you will have HF max, that is HFS max, this one is HFD max. That value I have told. From here to here there is a gradual variation. Why I am drawing this as a curved parabolic shape is, since the head loss due to friction is having a square term, that's why the variation will be, since the square term is there, the variation will be parabolic. In the other term it was single variation and not square term was not there, that's why it is having straight line variation. Here it is double parabolic variation since square term is there. So this is the effect of friction on the indicator diagram. And one more thing I have to add is, in the case of pressure due to acceleration of the piston, there was a triangle. Instead of this parabola, there was a triangle here and at the suction side. But if you are drawing the triangle, some area excluded from the rectangle is added to the other side. Therefore, total area of this rectangle is going to be constant. So work done is constant in the case of pressure due to acceleration. Even though some loss is there, but the total work done will remain constant, since the area of the indicator diagram remains constant. But here the area of indicator diagram is no longer constant. The rectangular area is there as such. To that area we are having two parabolic areas getting added, so the total work done will increase in the case of effect of friction on the indicator diagram. So in the case of first one, there won't be any change in the work done, but here there is a gradual change in the work done. Now combined indicator diagram. Here we will see both indicator effect of both acceleration of the piston and the frictional effect on the indicator diagram. I have already explained. Due to the effect of acceleration of the piston, the indicator diagram has changed to a shape like this, into a parallelogram shape like this. From a rectangular shape it has changed to a parallelogram. To that we are adding a parabolic shape here and a parabolic shape here. Since at the starting and ending of the suction and delivery stroke, the HF value will be always 0 and it will be having maximum value at the middle. So the combined indicator diagram is something like this. The ideal indicator diagram was a rectangle. Due to the effect of the acceleration of the piston, it has taken a shape of rhombus or some parallelogram like this. From To that parallelogram we are adding a parabolic shape. So this will be the combined effect, and in the starting and ending you can see that at the starting of the suction stroke the pressure inside the cylinder is HATM minus HS minus HAS. There is no HFS in the starting of the suction stroke. At the middle of the delivery stroke you can see here HATM minus HS, then we will reach point G dash. From here to here this is HFS max. There is no HF pressure due to HAS at the middle of the suction stroke. Pressure due to the acceleration at the middle of the suction stroke is 0. Therefore, here only frictional effect will be there. So, the pressure inside the total pressure inside the cylinder at the center of the stroke or the middle of the stroke will be HATM. HATM means here to here minus HS. This much is HS minus HFS. HFS max, that is A by A omega R, that 4FL by 2GD 4FLS by 2G ds into A by A omega or omega R whole square. That will be coming along with one. At the end of the stroke we will have again frictional head loss due to friction will be 0, but we will have HAS at the end of the stroke value will be there, but to the opposite side, that is at here the total pressure inside the cylinder at the end of the suction stroke will be HATM minus HS plus HAS. That will be the total pressure inside the cylinder. At the delivery side we will have HATM, here to here HATM plus HD plus HAD. At the end of the stroke there won't be any at the end of the delivery stroke again frictional head is 0. Therefore, the total head inside the cylinder is HATM plus HD minus HAD, and at the middle HAD value will be 0. So, we have the total pressure inside the cylinder as HATM plus HD plus HFD max. HFD maximum value you can calculate from the equation. Okay, this is all about the combined indicator diagram. Now, we will see a problem, university problem. The bore and stroke of a single acting reciprocating water pump are 20 cm and 30 cm. Bore diameter and stroke diameter is given. Bore diameter, since bore diameter is given, we can calculate the area of the cylinder using that diameter pi by 4 d square. Stroke length is 30 cm, L is equal to 30 cm. With that, you can calculate R, crank radius R, L by 2. And the pipe is 15 cm diameter and 10 cm suction pipe 15 cm diameter, ds is 15 cm and ls is 10 meter. The delivery pipe is 12 cm diameter, that means dd 12 cm and ld 28 meter. The pump is driven at 32 rpm, that is n. Determine the acceleration head and the frictional head. F is equal to 0.02 is given. Sketch the indicator diagram. That's our in both acceleration head and this frictional head we have to calculate, and we have to draw the indicator diagram. The suction and delivery head from the atmosphere are 4 meter and 60 meter respectively. That is HS and HD is given here directly. For HS is 4 meter and HD is 16 meter. Now, area of the cylinder we have calculated. Area of the suction pipe AS we have calculated. Area of the delivery pipe, cross section area of the delivery pipe we have calculated, and we have omega equal to 2 pi n by 60. That also we can directly calculate. Crank radius R is equal to L by 2. That also is directly available. Now, we have the equation HAS equal to pressure head due to acceleration at the suction side. HAS equal to LS by G A by A omega square R. We are calculating the maximum value only. Now, so on substituting, we will get this value as 3.06 meter. Now, delivery side pressure due to acceleration HAD equal to LD by G A by AD omega square R. On substitution, we will get as 13.35 meter. Now, we are calculating the frictional heads. HFS max equal to 4FL LS V square by 2GD. Instead of V square, we are substituting A by A is omega R whole square. Now, on calculation, you will get it as 0.218 meter. And similarly, HFD max 4FL D 4FLD V square by 2G DD. On substituting for V square, we get 1.85 meter. Now, this is the indicator diagram. You can draw here HS and HD. HS is given as 4 meter and HD 16 meter. Using that 4 meter and 16 meter above and below the horizontal line, that is HAT, we will draw a rectangle. From that, HAD is drawn upwards. Same value is taken from here downwards. Then you will get a inclined line here. Similarly, from the HS line, HAS value is taken upward, HAS value is taken downward. Then we will join. We will get the bottom inclined line. On that, we will draw a parabola. The maximum value at the center of that parabola is 1.85 meter, that is HFD max, and lower in the below portion we will get maximum HFS value as 0.218 meter. This is the indicator diagram.